Okay, so I think last example for the mixture. So if you have some composition, you have the percentage. You can take the mass fractions and then convert into moles and then mole fractions. Okay? And you'll have the mole fractions as in each component. Okay? And then okay. So usually if you are setting this as the percentage, of course we are going to have the basis, right? The basis of calculation, which means the total amount of usually the mass of the mixture. Okay? So usually if it is in percent, you can assume or using the 100 basis. This is the most usual case or calculations. Okay, now after we know the composition, the next thing is the average molecular weight. Okay, and usually it's really important if you are dealing with some experimentals. Okay, some experiments, especially if they are really consider about the molecular weight. Because, for example, some polymers, okay, even though it's the same polymer, it can be or it can have a degree of variation. Like maybe the average molecular weight can be different, like maybe thousands or maybe 10,000, 20,000, and the property will be different also. Okay, so that's still important. And to calculate the average molecular weight, so let me write here. So average molecular weight. Molecular weight. Or mean molecular weight, but usually it's frequently used or oftenly used average molecular weight. Okay, we are usually state this by this symbols, and the unit will be kilogram over kilomole, or if you are in the UK standards or the American standards, and there are others that I think still, but usually just the first one is I think good enough. Okay, and we can denote this molecular weight, the average molecular weight, by this formula. Or we can write in terms of the summations of each component. So means that this is all components. And the y is the mole fraction. So the same symbols as we mentioned before. Mole fraction of each component, or let me write in terms of a random component like this one. Okay. And then the m is the molecular weight. And by taking 1 mole of mixtures, we can also get the 1 over m or this is 1 over m, the average molecular weight. We use reciprocal. We take the reciprocal and change the mole into mass. Okay. And this is also similar, but this is for mass fraction. This is also denotes that this is all components. And let me just write here that the x means the mass fraction. Okay. I think intuitively it's kind of easy to understand the average molecular weight. So which means that if you have a component, you have like several elements inside those components. You can then observe each one of them and observe each molecular weight, and then you can have some average through this formulations. Okay. Okay. I think sample. I think no need for example. I think it's quite clear. I think. Okay. Aside from the molecular weight, other important chemical related or chemistry related is the concentration. By the way, anyone joining the laboratory already? Already joined? Okay. Anyone else? Not yet? Maybe Jory already joined, right? Okay. So usually, are you deal with the polymers or any chemicals? Biomaterial, but is it polymer?
Cellulose.
Cellulose, yeah, it's polymer. How about you, Muse? Also polymer or different? Nanoparticle. So inorganic, or is there any organic material inside?
I think it's organic.
So do you deal with the chemical compounds, like maybe from the, like you open from the bottle and then you look? Usually, if you look on the chemical compounds like in the bottle or in the jar, they will have certain descriptions, right? And usually they have the internet-based descriptions, the MSDS, right? And you will see some I think in most cases the polymer, they have the molecular weight, right? Usually they will have like big numbers, right? 20,000, 10,000, or maybe a small number, 1,000, 2,000, something, right? Usually. So I think if you look on those polymers and you realize that the polymer has a long chain, and then it depends on the elements. You can imagine how to calculate those. And of course, if you try to calculate manually, it will be a really tedious job, right? So there are several methods to calculate automatically. Okay? So usually it's related to some analysis. but anyway, the other thing is the concentration. So we have at least mass concentration. This means this mass divided by volume, or we have the more frequent or the more often the molar concentration, right? So this will be the moles, or let me just write moles and then divide by volume. And we call, or we can write this as a molarity. This is value of molar concentration of the solute. Expressed in gram moles per liter solution. So maybe check here. So if you have 0.02 molar solution, let's say this is the natrium hydroxide, and then 5 liter of this solution contains, so 5 liter multiplied by 0.02 mole per liter, so it will be 0.1 mole natrium hydroxide, and if it is having some flows, like it has some rate, you can also calculate the molar flow rate, or maybe I will give you the idea how to converge the mass, molar, and volumetric flow rates. Okay, let me go to the next page here. So mass, molar, and volumetric flow rates. So you have the questions, maybe example. 0.5 molar aqueous solution of sulfuric acid flows into a process unit at a rate of 1.25 meter cubes per 1 minute. Specific gravity is 1.03. Okay. calculate mass concentration in kilogram over meter cubes, and then calculate mass flow rate of the compounds in kilogram per second, and then calculate mass fraction. Of course, we need some database, at least the molecular weight, right? Let's say the molecular weight, the weight is 98. Okay. So first, we can write down that the molar is 0.5, so this will be mole per liter, right? So we have 0. Let me write. So 0.5 mole per liter, right? And then we need to convert this mole into the kilogram per meter cubes, right? So at least we need to have the 98. It already have the gram, right? Gram, and then per mole, right? So what we need is we need to have the meter cube, right? The meter cube we can have from the liter. So eventually, okay, if you really really observe only the unit itself, you can figure out actually what's the formulations. Okay, so see here the mole already cancelled here, so we need to convert the gram into kilogram. So we need to convert to different color, kilogram. We need to divide by 1,000, right, to convert this, right? And then to convert the liter, we need to convert and multiply, because liter is decimeter, right? Decimeter cube, right? Okay. Now from here, when we are observing this value, we get that our term is kilogram per meter cube. Okay. So whenever you have like any calculations in your mind, and then you want to make sure that it's correct, look at the units. Look at the units. That's the most essentials, okay, as an engineer. So if you maybe probably clueless, or maybe you probably forget which formula you want to use, it's A, it's B, you can try to figure out through the units first. That's the sense of engineering. Okay? Sense of engineering. Okay? Try to look at the units. Okay, that's how it works. Okay. So basically this is what we are having. Okay. So this is mass concentration of the sulfuric acid. I think you can just type in it's around half 49, right? 49. And then the flow rate. The flow rate, it should have kilogram over second. But you have in your questions, you have the 1.25 meter cube over minute. So you need to change the minute into seconds, right? So let's just write as it is. The flow rate is 1.25 meter cube per minute. Okay. And then because it's asking mass, how we can get the mass? We can get mass just from the previous questions, right? We have mass concentration, so we just took the mass concentrations. We took in, and you see that there we just only observing the units, okay. And then we can convert the minute to seconds. So 1 minute convert to second. And then we can have the cancellations, and then this is what we get, or we can have this is the molar, not molar, sorry, mass flow rate of the sulfuric acid. So this will be 600 should be one something. One 25 divided by 6 is around 2. 2 divided by around 2 should be 1, right? Should be 1 something, or it's 1. Okay. Yeah, should be 1, right? Because if you use the because 49 is half of 98, which is nearby 100. So if you take 100 to 1.25, it's around 125 divided by 60 is around 2, but it's twice, so it should be 1 or 1 something. But I think it's 1, right? Okay, now the mass fractions. Now this is because we need to have the fixed property from sulfuric acid. We need to use the specific gravity, right? You need to use the specific gravity. So we need to use the specific gravity to get at least the density. Okay? So the density of the solution, we can use the given information 1.03 and then multiply with 1,000 kilogram or metric cubes. That's the water density. And then we can have the flow rate. Flow rate of the solution. Multiply with the density. And then change the minute into second. So this is the total solution. The total solution. So the mass fraction of the sulfuric acid is, we can use the flow rate. So 1 divided by 21.46. This is only the sulfuric acid. This is the solution. So we get the mass fractions. Okay, so this is number C, this is B, this is A. Let's say A, B, and C. So for the first two numbers, or the first two questions, it's asking only the compound itself. Okay, the compound itself. For number 3, it's asking the solution, because we need to know the density. Because we want to know the mass fraction of the sulfuric acid compare with the total solution inside. So we assume, or we imagine, the total solution inside. We are just converting the specific gravity from the given information. Okay. Yes?
I thought mass fraction is dimensionless. Mass fraction is dimensionless.
Yeah, this is just to note that this is what we are targeting. It's actually dimensionless. Because sometimes you have like different mass fraction, different compounds, right? Just to note that which one is which. Yeah, I think generally, like in the general chemistry, actually you can just write just a number, because basically it's dimensionless. So there is no specific written text on mass fraction. Okay? As long as you mention clearly that which mass fraction you are calculating. Okay. Aside from the concentration, there are also some terms. It's called the parts per million and parts per billion. I believe you already learned in chemistry also, right? This is just to note that you can also write like 2 ppm, 2 ppb, or something like that. But actually in the real industry now, it's not really mentioned a lot. But this is just to note that we have these terms. Okay? So we can have ppm, each component, like maybe we can write same terms with the fraction, or ppb. And I believe this is quite conventional. Okay. It's really maybe in 80s or 90s. And there was, you know why sometimes we are not really using this ppm, ppb? Because there are some different terms or definition in American definition and the UK definition of billions. Like, is it 10 to 9 or 10 to 12? But because of that confusion, sometimes people just skip this and using the numbers instead, not using the PPB or PPM. Okay. Like the confusion in terms of like inch, feet, inches, feet. The usually if you go to or if you heard like someone from United States, they will like measure something with how long it's 10 inch. Okay. Yeah, but yeah, that's some terms. Okay, we can move to, I think, two last sections, the pressure and the temperature. Pressure, as in physics that you might have learned, this is the ratio between the force and the area. So we can have the unit as Newton divided by meter squared, or pounds, inch, or psi. And usually we call the Newton over meter squared, we call Pascal. And usually in terms of measurement, we can have some, if you calculate the measurement of metals, okay, how strong it is, usually it's in the terms of Pascal, like MPa, GPa, gigapascal, megapascal, because of the metals is quite strong. But here we are just focusing on more about fluids, okay, fluids, not solid. Okay. So we consider the fluids is in the pipeline, right? It's stream like that, and it has some pressure. So we call this the fluid pressure, defined as the ratio of force divided by area. The force, we can imagine that it is a minimum force that would be exerted or applied, okay, to keep the fluid from emerging. And of course, because we are involving the environment, in our case here, this will be related to atmosphere, because our atmosphere is also fluid, right? It also contains air, right? So we can have fluids in tanks like this. Okay. So it is the force, and then this will be the cross sections, the area. So the force Or if we imagine like a pipe, this is some force here, and then this is the cross section, and then this will be the pressure. Okay, suppose the fluid or fluid density, it has a kilogram divided by a meter cube, and pressure, let's say the pressure P0 is exerted on the upper surface of the column. Or maybe let me just draw. Okay, this is similar with the first picture, but it has exerted force here. So let's say this is P0, and it has some certain height, and you have this fluid density, kilogram, and you have the area here, the cross-section area, and you will have the fluid pressure at the bottom of the column. Okay. Now the idea or the definition is to the pressure, or P. So pressure P at the base of column is called hydrostatic pressure. By definitions, this is the force F exerted on the base divided by A, or base area. And F itself equal the force on surface plus weight of the fluid. And then if you using some terms from force, some mass, you can convert it into the P equal P0 plus rho GH. So you can imagine this. If you want to tweak this, the formula, you can imagine this, okay? And also remember that in volume you have the area multiplied by h, right? So h is volume divided by area. If you try to tweak this, you will see you can actually get these formulations based on the force. So the force itself equals the force on the surface plus the weight of the fluid, and the weight of the fluid you can convert into the volume using the density, right? Using the density, and you can get this formulation. Okay. And sometimes to express the pressure, we can also express the pressure as the head of some particular fluids, like a head. Okay. So if you have 14.7 psi. Equivalently, 33.9 feet of water or H2O, or 76 centimeter of mercury, or Hg, mercury. And if you want to know the height itself, if the pressure on the surface is 0, so if the pressure on the surface is 0, which means the P0 is 0, that means that P, as in the force divided by area, this will just density of the fluid, gravity, and the pH, or head of fluid. Which means it's correlate with the height. Actually, that's the same meaning. So when you read like using the mercury, that means that it's the height of the mercury, right? The height itself when you read the scale. So we can use that height in terms of the pressure head. In terms of pressure head. Do you get what I mean? So it's mean that if you familiar with the scale for the pressure, like a bar, usually maybe the mercury one, okay? We call that pressure, right? Pressure, but we use the terms the height itself, okay? Which means they are calculating as in the this top surface is 0. So what they're calculating is the height. And usually the height, when we calculate, we usually use terms pH, the pressure head. So it's actually the height itself. Okay. Usually we calculate as the height itself. Okay. Okay, let me show you the expression. Okay, maybe wait for a few minutes if you want to take some notes here. Okay, let me go for a while, okay, and then maybe later at the end of the section on pressure and temperature, we can have maybe some short break. Okay, let me explain more, okay, about the pressure head, if you would like. So if you have 2 Pascal, okay, we want to write this in terms of millimeter mercury. Okay. Assume that gravity is 9.8 something, right? And then density of mercury is 13.6. Or let me just write the whole number. 13,600 kilogram over meter cubes. So the pressure head, as we mentioned, we can write as in terms of rho, or maybe from here we write as I write in the last slide like this, right? Okay, we can write and solve the pressure head, okay, and then write down. So write all the units. Okay, again, units play important parts. Divide by the 9.8 meters second squared, and then 1. This is the conversion, and also conversion for millimeter. So we can write so basically the pH or the pressure head in terms of, let's say, millimeter mercury or other units that in it can be a PSI or any units. This means that this is actually so this is the relationship between the base of column pressure and the surface pressure. And we refer all this pressure as the absolute pressure, but actually there are some additional elements that need to be considered. That is the atmosphere. And standard for 1 atmosphere, I think you already know, that is the pressure at sea level, 760 millimeter mercury. So the absolute or pressure absolute is P gauge. Gauge pressure is measured by device. So relative to atmosphere. And then there are several devices as mentioned. The most common one is the Bourdon gauge and manometer. Bourdon gauge is like a watch, like that, and it has some scale like that. Manometer, there are at least 3 types manometer. So basically the manometer works like okay, let's say this is, you have some fluids, and then you have, we call manometer fluid. It says, I should be taking a little bit down. Okay. So this is the fluid or manometer fluid. Okay, so basically how it works is we are just taking numbers between pressure as in P1 and P2, okay? And we can see the difference on the scale. Okay? So you will see the scale as in terms of different height. Okay? This will give you some idea from this, okay? From different height. So of course, different pressure, it will have different height. And if this is just an open air for the pressure 2, this is called the open end. Okay. If it is connected back to the pipe, then it's called the just differential. So it's going back like that. And we say this is the difference here, and we can call this difference. This is differential manometer. So we have P1, we have P2, and if P2 is 0, or we sealed the pressure, we call this is the sealed end. Okay. And sometimes the fluids may be different. Okay, it's fluid 1 and 2. It can be the same. It can be different, and we can generate into some formulations in general manometer formula. Okay, so let me just write in the terms. Let's say we have 2 and let's say this is the fluid. Okay, and you have a fluid here that is let's say row 1, and maybe different color here. This is row 2, and let's say this is A and B as our observation here. Now based on our general formula, then we can take the P1 and then plus with the fluid 1, the row 1, right? Plus row 1 gravity and the D1 as in height, and we can take this into equations. So equates with the second fluids, and then this is the fluid of the manometer. So we have a manometer fluid here, okay, and we can have this general formula. Okay. And of course, you can have some variations. For example, if row 1 equal row 2, you can have different terms. And I think just taking one general formula is, I think, basically enough for understanding the manometer. And for gases, the formula is just this. Okay. Manometer for gas. Okay. So regarding this pressure, I think I will just give you some additional lectures. Okay. Maybe just giving you the video for like maybe 10-15 minutes to help you getting understanding in pressures. Okay. But this is basically what pressure is. There's not really much sections in pressure. Okay. The last part is the temperature. The definitions of the temperature, okay, like you say it's cold, hot, cold, warm, right? So basically, it's average, the measurement of the average of kinetic energy. that can be measured. Of course, what we measured is not directly the energy itself, right? Because we are actually, if you think about energy, we don't really actually understand. I think every engineer, every scientist that comes up with the theory of energy, they haven't really understand the energy itself. They can apply the energy, convert them into something else, but the definition of how to measure the energy directly still not really that sophisticated be done. Okay? But we can measure when it is converted. Like for example, the temperature. It's converted into our sensations of cold, hot, warm, right? We can say, oh, it's hot. Or probably there's a lot of energy inside it. But actually, how much is it? What we can do is we can approach the numbers, maybe with joules, the terms joules and so on. But eventually, we still not really know, actually. Okay, so I think in the textbook they mentioned some device based on temperature measuring device like thermocouple, pyrometer, or even just a regular thermometer. I think that's quite common, and I think you already know. What is important is, I think you need to know the scale, right? The scale, like the Celsius, freezing and boiling, and then absolute zero. Some terms that probably have some meaning in our case in engineering. So lowest temperature in nature. This is lowest temperature in nature that we can observe. We are not sure if there are any lower than the absolute zero. So absolute zero is around this number. And then there are other scale that usually, again, I think American use more, Fahrenheit. The difference is they are using some 32 degree difference. And absolute zero, it's also different. So, because there is much numbers, we need to come up with another scale that are easy to compute. It's called the Kelvin, right? Kelvin or K, and Rankine for Fahrenheit. So why we are using Kelvin and Rankine? Because they have the absolute zero. So that's why when you compute the Celsius and then convert into Kelvin, you need to use the number 273, right? 273, because that is actually the absolute zero. Okay. I think some conversions, like I mentioned, this is the Celsius. R is in the Rankine. Okay. K is Kelvin. Plus 32. There are some mentioning the heat capacity in this book, but I think that is more in later part on our chapters, the heat capacity. So I will just stop here for temperature. Okay. So I think that's it for the whole process and at least the process variables. So we'll start from mass, volume, right? And then the density, specific gravity. And then move on to the fraction, mass fraction. Oh, we move to flow rate. Flow rate first because we are usually in our case, the most or the oftenly used terms are mostly all about fluids, either the gas, okay, or fluids itself. And we are having the flow rate, concentration, and then the pressure and the temperature. So this is all the terms that usually we are going to consider in our calculations. Either we calculate how much amount of energy we are going to exert or the process, or the balance on the material itself, either the mass, the chemical compounds or any other parts. Okay, so I will stop the recording.